Assalamualaikum and hi. My name is Muhammad Haziq bin Shahril, currently in my third year pursuing industrial chemistry. So today, I'm going to present on optimization of instrument conditions for the analysis of mercury, arsenic, antimony, and selenium by atomic absorption spectroscopy. So let's start. So first is the abstract. We use the chemical vapor generation atomic absorption spectroscopy technique because it is extremely popular for tracing analysis, specifically hydride generation continuous flow system for arsenic, antimony, selenium, and cold vapor for mercury. But first, we have to optimize the parameter which will increase the production of hydride or vapor species form, thereby improving recoveries. The parameters include reagent, sample and argon flow rate, acetylene A ratio, concentration of reagent, and rate delay time. It will also increase and reduce the chemical interference for other species that may compete with the analytes of interest for hydride formations. The optimized flow rate for all reagent was between 0.9 to 1 milliliter per minute, between 6 to 7 ml per minute. The optimized type and concentration of reducing agent for arsenic, antimony, and selenium were NaBH4 0.6% weight per volume, 0.7% weight per volume, and 0.1% weight per volume in NaOH of 0.5% weight per volume respectively. As for the mercury, we use SnCl2, 25% weight per volume in HCl. Next is the method details method. Chemical vapor generation techniques actually include hydride generation, atomic absorption spectroscopy or HGAAS, and cold vapor atomic absorption spectroscopy CVAAS. It will do the separation of the analyte from the matrix by conversion to the volatile hydrides and offer a pathway to trace analysis of elements such as AS, SB, and SE that cannot be determined by conventional method. Low level of detection or LOD are attained when this separation method is combined and atomization of the hydride is heated in a quartz tube. So HGAAS techniques actually involve three distinct processes. The first one, it releases the element of interest from the sample solution, which then will convert it from hydride to the gaseous phase with the aid of reducing agent. Next is hydride collection, and the third one is atomization, which is the transport of released hydride to the atomizer by the flow of an inert purge gas. Factors that influence the yield of hydrides and sensitivity of the techniques includes concentration and type of the acid and reducing agent, and the flow rate of the carrier gas, reducing agent, acid, and also the delay time of the sample. Other than that, we know that mercury it uses alternative absorption technique such as cold vapor atomic absorption spectroscopy or CVAS, because it is very sensitive method for mercury determination. This is due to mercury determination through flame atomic absorption spectroscopy will only give rise to a very poor sensitivity. So we have to use CVAS for mercury. So the principle of cold vapor AS, a reducing agent, usually we use SnCl2, is used to convert ionic metal ion of Hg aqueous in solution to Hg gas, which produce a higher analytical absorbance signal. Mercury also have high vapor pressure, which will be liberated and entrained in an inert gas of argon after passing in the liquid gas separator. The mercury vapor then will be transferred into the optical path of the atomic absorption spectrophotometer, where mercury absorbs light of a specific wavelength at room temperature. Actually, we can maximize the sensitivity and precision by optimizing the parameters, and the parameters includes concentration of reducing agent, flow rate of reducing agent, which is SNCL2, flow rate of sample, purge gas, and the read delay time. So here is the schematic diagram for the VGA accessory coupled to the AAS, to the atomic absorption spectrophotometer, and the optimization parameter for HGAS and CVAAS. So I'm going to explain a little bit briefly on the experimental procedure. So first we have the calibration standard of 10, 30 and 50 part per billion were prepared for each metal, which is then being analyzed in a 50 ml of volumetric flask. And then mercury was optimized. Why we need to optimize first? Since potassium iodide used to reduce AS, SB and SE has a negative interference on mercury. Next, we have to the varying concentration of reducing agent and acid solution were prepared in a volumetric flask by weighing the appropriate masses of the reagent, and then we dilute it to 250 ml with the deionized water. The deionized water then will pump through the entire system of 60 seconds between the analyzers. And next, we have to make sure that AS was zeroed after each modification, and absorbance were measured for each variation in the solution. Adjustment knob was tightened or released. This is to modify the flow rate. And next, the specific uptake tube for the respective solution, which include reducing agent, acid and sample, was placed in 25 ml measuring cylinder, and the volume of the reagent used in 60 seconds was determined by the flow rate. Next we have to make sure that the pump tubing internal diameter was also varied. We have to vary the pump tubing internal diameter so that we have the opportunity to control the effect of the flow rate. The temperature then of the air acetylene flame was optimized by HGAAS by regulating the flow rate liter per minute of the acetylene gas to oxidant. We also have to make sure that the tubing of the sample was kept constant at 2.28 mm, and the pump tubing for the acid and reductant were varied. We also have to make sure that the instrument was zeroed after each adjustment. And lastly, we can actually analyze the absorbance of the sample, which will then be recorded for each change in flow rate of the acetylene gas and argon. All conditions were kept constant during the analysis, but only the parameter stated before being optimized and varied. Next, for the discussion, we know that the reductant concentration actually had an important influence on signal intensity because it affects the hydride generation process, which converting the oxidation state of the element to the very or most stable lower oxidation state. The reduced ion form the stable hydride, which are very needed for the HGAS. Optimum concentration of reducing agent used for arsenic and antimony was 0.6% weight per volume, and ABH4 in 0.5% weight per volume, and AOH. For selenium, the optimum reducing agent was 0.1% weight per volume, and ABH4 in 0.5% weight per volume, and AOH. And for mercury, as we all know, the most efficient reducing agent used and well established to be is SNCL2, and the optimum concentration was found to be 25% weight per volume, SNCL2 in 20% HCl. So here in the table, it actually summarized the optimized condition for each parameter selected for each metal. Includes arsenic, antimony, selenium, and mercury. That's all for me. I hope you enjoy my presentation and video. Thank you so much. Assalamualaikum.